Okay. I am set with coughing. I have no idea why, if it's some sort of allergy, but at least it's snowing tomorrow, and therefore all the allergens will go away. Welcome to RocPy, our one and only, and still the one and only, and always will be the one and only Python user group. And any others are just imitation. And I do not have the right fonts. This computer, I think I had the same problem before. This list should probably be shrunk down.
Yeah, by a couple.
Yeah, here. Let's do that right now. I think Dave is probably okay not being
here. Dave's out on the high seas.
Yeah, and I think Emily is okay too.
I haven't seen Emily in many months.
George.
Yep.
George Adams. Okay, and I'll fix this later. Fix it in post. Organizers, I've been sort of away for a while, mainly pandemic and new job and all sorts of stuff like that make it difficult for me to catch up on things, but I'm trying to make a good effort. I'm looking forward to coming back in person to be with all of you, and I'm assuming Josh, when that happens, we're coming back to Innovative.
Yep. Yeah.
Right. Awesome.
That's the plan.
So along with all you guys, and tell you about our mission to promote, protect, and advance Python and support and facilitate the growth of a local community of Python programmers. And, sometimes it doesn't have to be just about Python. We all like to talk about technology and so forth. So sometimes we have accessory things that have tangential Python applicability, like, databases aren't by Python by themselves, or key value stores or APIs or whatever, but sometimes you find a good reason to glue together these systems with Python. So it's worth it to foster a community of people using Python. We have a bunch of infrastructure. I don't know what to say. I migrated my personal server the other day, so the RocPy website was down, but it's not back up. It still looks as crappy as ever. And Meetup long ago did away with the domain forwarding, so I was just going to forward it on to Meetup. I may just do that with JavaScript or a redirect in Apache, but I mean, do we see need? Should we make a call out for a web dev to fix things for us? I don't know.
Yeah, well, we can have that conversation, but I think it's still a valuable landing page outside of Meetup.
You're very kind. Yes, I'm the one that made it, so I know look at it with distaste. IRC, I think I still have a bot that pretends to sit in the channel and do listen to things. So I should probably check on that. I doubt anyone's in there, but I do love my IRC. But we have Meetup, and Meetup is our primary method of communication with everybody. And it's worked out well for us, thanks to Josh. And, he's maintained it for all these years and kept it going for us. And we have GitHub, but I think we use that sparingly.
Yeah, it's got a couple of projects out on it.
Yeah. And that said, as I just mentioned about the website, we're always looking for help. We don't pay much. We pay with gratitude and, and love. So if you're willing to help and contribute both in talks or content or, a helping hand, we very much appreciate it. I have no idea what happened last time at RocPy. I'm ashamed to say.
I actually gave a talk on Git.
Oh, I do remember that. Yeah, I was there. I didn't miss it. Haha. We gave a talk on Git. Yeah, Josh did. So it was pretty good.
And I do finally have that video up on YouTube.
Wonderful. Let's see. In tonight's episode, Fred is going to talk about some data pipeline for an observatory that I don't even know the backstory there. So I'll leave it up to him to explain. But when I see data pipeline, I enjoy. I'm excited to hear about it. I love that sort of thing. And Fred is an astronomer. Right? You're still an astronomer, right? Excellent.
Supposedly, but at least I play one on TV.
I play one in real life. But you're at RIT, correct?
No, I still work on the telescope project, but I'm actually a third-party contractor. So okay. I'm out of my basement.
Got it. Okay. It's been a while since we spoke, but this will be fun, and I've got a couple of people in the chat. Maybe George would be cool to putting the RocPy site stuff on the rock.dev website, possibly. Well, we have a domain, so I think we'd rather just use our domain for that reason. And if he wants to forward a link there, that'd be fine.
Yeah, or also have a blurb on the RocDev.
Yeah. Yeah, any sort of promotion is great. Absolutely.
My thought was that if you're going to be getting rid of it and just forwarding to Meetup, maybe having something on RocDev would be a better alternative for that. But whatever.
Yeah. I mean, it's a matter of someone creating the aesthetic content. You know, it's just, as Josh said, it's just a landing page. And, 1990s web dev chic is not in vogue right now. So we got to do something a little different. Anyway, so let's get to tonight's show. If you want to contact us, org at rockpy.org, and we should have a working contact form as well on the website. If you want to help, you want to contribute, whatever you want. So thank you for listening. Fred, hand it off to you. You want to share the screen?
All right, thanks, Rich. Yeah, so, well, it's kind of funny, right? How like we're in the middle of a pandemic, we have all this free time, and yet we seem kind of busier than ever. And so, like, I started putting slides together for this, just the other day, and I don't know that I necessarily have a half hour, an hour of content. I have 22 slides. I have some stuff mixed in, so we'll see. Feel free to ask questions as we go, and we'll see how that goes.
I'm sure it'll be fine.
So let me share my screen. Okay. Can everybody see the presentation now?
Yep.
All right, great. Okay, yeah, so I'm going to be talking about the data management science pipelines for the Rubin Observatory. And so the Rubin Observatory it's an observatory they're building in Chile. And so it was supposed to be completed this year, but then COVID kind of hit, and Chile was hit pretty hard. And so, pretty much as soon as COVID hit, they hadn't been able to work on it and just started being able to get back up to the mountain a couple months ago. And so, that's putting a pretty good delay. They had to lock everything down for the winter in Chile. They hadn't finished the dome yet. And so they had to cover all the equipment and everything that was kind of exposed at the time. And so it was slated to begin like late this year, early next year. Now they're looking late 2023, early 2024 with all the setbacks and everything. But once the telescope is finally built and working, it's basically going to take a 10-year movie of the entire southern sky. So everything that you can see from the mountains in Chile. And so what that means is essentially the telescope's going to spend all night long, slewing and taking images of the sky, and it's just going to keep revisiting the same areas over and over again, as often as possible, so that we can, get a better understanding of, what the universe looks like. Part of the 10 years is you catch a lot of transient things, so you catch things that are changing in time. But also, if you take an image of the same patch of sky over and over again, you can get kind of deeper and deeper images, meaning you can see things that are further away. And so, most astronomy that's done over the next couple of decades is going to be using this in one form or another. And so it's going to generate about 1.3 petabytes per year. And then that's going to continue on for 10 years. And then access to that full data set is going to be available to all US researchers and US institutions, as well as some foreign countries that have science agreements. And so, so that's really good news, is that, even if you're at a small university, a large university, doesn't matter, you'll have access to the data. So the actual telescope is an 8.4 meter telescope. And it's so large that it actually has these magnetic motors, so that it can very quickly and smoothly slew from one spot to another. I believe I can't remember what the time frame is, but it's some ridiculous time frame that they're gonna switch from one image, one site to another. It's within a minute. And then it's going to have adaptive optics that are going to change the shape of the mirrors. And so there's all sorts of software that's going to be controlling this. None of that's what I'm talking about. That's all, written by a lot of it's in like LabVIEW or whatever crazy stuff they put together with that. The mirrors, so there's actually 3 different mirrors. So the larger mirror, which you see here, so this is M1. So light essentially is going to come down from the top. It's going to hit the larger mirror, which is going to be reflected on M2 above it. That's going to be reflected down onto M3, which sits inside of the larger primary mirror. And then that's going to be reflected back up to the camera and focus with some lenses. The mounting assembly for this, there's actually a few different mounting components. One of them was made right here in Rochester by L3 Harris. And L3 Harris also made the M2 mirror. I don't know if that was made in Rochester or one of their other sites. But typically I don't show pictures of all the mirrors, but I figured since one of them had a local connection, I'd show that here.
If Dave Rhodes was here, do you know Dave? I don't know if you've
I do, yeah.
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 I know he works for Harris, so I don't know if he would know anything more about.
He would probably know. If it was here, he probably saw it, I'm guessing.
Yeah.
Because that seems like the thing you'd stop by and see.
Cool.
But okay, and then there's the camera, right? It's a 3200 megapixel camera. So there's 121 rafts, and each raft has 9 CCDs on it, and each CCD is 4K by 4K. And so here's an image over here of the full focal plane, and you can see, this is what the moon would look like on here. So that gives you, just kind of a feeling for just how big a single image from this thing is going to be, and why this is why it's going to be able to do such an expansive survey, is just because it can cover such a wide area. And part of that, so you may be wondering, because this isn't that large of a telescope, so why is it that you can see such a wide area? And it has to do with kind of the shape of the mirror, what's called the I can't pronounce it properly, but the entendu. And so essentially it's not as curved as a mirror would normally be. So it's like a special shape that allows you to gather light from a wider area and focus it in and catch it in there. Okay, but what I'm going to be talking about today are the science pipelines, or also known as the stack. And so this is a collection of it's several hundred Python packages, but effectively it's about 100 Python packages that we develop and maintain. That's only for analyzing the data on the LSST. So again, this has nothing to do with operating the telescope or the camera or anything else. This is just the software after they've taken the images to clean the images and to stack them together and to analyze them for stars and galaxies and everything. And so just to kind of take a look. So this is the GitHub page, and so you can see there's 429 repositories. Part of the reason that number is so large is because when the project was started and they wanted to make sure that they had good control over reproducibility, essentially every third-party package was ported to be wrapped in the stack and was updated. So that way, you could at any time go back to a different version and have all the third-party packages and everything be the correct version. And so out of that 429, there's probably only about 100 that we actively maintain and develop, and everything else is from outside. And so there's 2 main components to the science pipelines. So the first is the alert processing. And so this is essentially like every time an image is taken, within 60 seconds, they expect there to be about 20,000 alerts that are generated based on that, in terms of transient stars and possibly supernova, just all sorts of events. Again, most of those aren't going to be of interest to most people, but just based on the field of view and the number of objects per field, that's about what they expect. And so that's the first part of it. And then the second part of it's the data release processing. And so this is going to be released, just about annually. And so this is going to be kind of what builds up that movie over time of the sky. But both of those components share the same data processing pipeline. It's been built because a lot of them need a lot of the same components. And so instead of trying to keep two different repositories, there's just kind of one master pipeline. So developers, even before COVID, were spread all over the country. The main two places is the alert processing is being done primarily by the University of Washington. The data release processing is being done at Princeton University. And so I got involved in this when I was a postdoc at Princeton. And, essentially, when my wife wanted to move back to Rochester and got tired of living in New Jersey, they allowed me to move back and work from home. And there's actually a number of other people who do that too. So the project has been kind of big on just trying to get the people they can get and working around, where they want to live, because not everybody wants to live in Seattle or, Central Jersey. And so, so all the code is open source. It's available at github.com/LSST. And then there's another set of repositories at LSST-DM. So the official pipeline is the one at LSST. Kind of as things are being worked on, they're usually in the LSST-DM namespace, and then get ported over once they've been vetted a bit more. So just a little bit of history. So the development began in about 2004. And so it was based on the pipeline for a previous survey, the Sloan Digital Sky Survey, which was mostly written in C++. And so to kind of give you an idea of what was going on in Python at the time, so this predates NumPy by about a year. It predates virtual environment by about 3 years, pandas by about 4. Pip, the current namespace is pip, by 7 years, although there was kind of an earlier version in 2008. Anaconda and AstroPy were 8 years later. And so as I talk about some of the things, keep in mind that part of the reason that things are the way they are is because all of the things that are kind of standard in the Python community now, we didn't have access to at the time. I was still an undergraduate, so I wasn't doing any of this at all, but the people working on it and who started this. And so this moved from Subversion to Git in 2011. It became available on GitHub since 2015. And then in 2016, it was ported to Python 3, which was a very contentious argument at the time. I kind of walked into this big debate. People were saying they didn't want to waste the time to do the Python 3 port. And other people were saying, well, Python 2 is already going to be obsolete and not supported by the time the survey starts. So it seems kind of silly. But as those of you who work in larger companies know, it doesn't always have to make sense. But okay, so on the C++ side, because of the fact that it was developed before NumPy and before there was a really good way to handle large arrays in Python, or at least a largely accepted way, most of the primitives are still written in C++. So all of the image arrays, all of the catalogs, a lot of the mathematical statistics packages, the data persistence, date time, all of that's all written in C++. And we're still kind of paying the price for that today. So as of 2018, there's about 225,000 lines of C++ code in the stack. Originally, that was wrapped in the SCons package. But then in 2017, we ported this to PyBind 11. And I'll show a little bit of that code in a little bit. Actually, I don't know, I was going to do that here. So if you've never seen PyBind 11 before, what that looks like. So this is like just a really simple module that just has a couple functions. So these are written in C++. And then essentially you have this one wrapper here that says, it declares it as a PyBind 11 plugin macro. And then it sets up, this is the Python module name. And then you essentially wrap each function. This is just the defining eigenmatrices. So eigen is a good C++ library. Essentially, this is what, if you have a NumPy array, you would port it over to eigen in C++. And so like this is the one function. So like you just wrap the function, you give it the doc string, and that's all there is to it. The thing with PyBind 11 is you have to do the same thing if you have a class. So for example, if you have a class, so for example, this is a footprint class, you have to wrap everything. You have to wrap all of the getters and setters. You have to wrap all of the methods. Now you can, one of the nice things is you can take a getter and wrap that as a property. And so you can have access to, in Python, this pretty much acts just like a property. If you wrap both the getter and the setter in that. But it was quite a tedious process to have to go back and wrap every single thing in PyBind 11, but it really kind of cleaned up our build process after we did that.
So why was that? Why did it clean? How did it clean it up?
So I don't know if you've ever used scons before. So scons is something that's supposed to kind of, the idea of it is supposed to kind of automatically wrap all your C++ classes and functions. And when it works, it's really convenient and easy because you tell it to wrap everything and it does, and you're good to go. The problem is if there's any problems or if there's anything strange about the objects in C++, it takes a lot of monkey patching and a lot of work to make it together, to put everything together. And so for some of our packages, some of the ones that had like our really early C++ primitives, it just took forever to build. Whereas
Gotcha.
once we switched to PyBind 11, the compiler could do a much better job of figuring out what it was supposed to do.
Gotcha.
But this is far from my end of expertise. Like I can code in C++,
Okay.
and then for all this wrapping, I kind of do what I'm told, and that mostly worked.
Cool. Thank you.
Mm-hmm. Okay, so on the Python side, there's about 290,000 lines of Python code. And so again, like I said before, for reproducibility, originally all the Python packages were stored in the GitHub repo. As of 2019, we switched to CondaForge, and so we have a tagged environment for each release. And we have releases every, where there's a release every day, and then there's a weekly release every week. But one of the things that they wanted to do is split it up. And so instead of having just kind of like one large or a few large packages, everything's in a small package. But so for example, there's the pipe_base package. But if you actually, when you import in Python, the namespace that you get is actually lsst.pipe.base. And then pipe algorithms would be lsst.pipe.algorithms. So it still shares the same common namespace. And that's what the scons part that still builds that namespace. And then over time, some people like myself have been trying to port as much of the C++ functionality back into Python that we can, because I found that it makes it run faster and in some cases, and is obviously much easier to maintain and read through. So I wanted to talk a little bit about some of the advantage of having a lot of small packages like this, because I've talked to a lot of people who are starting kind of larger projects, and they're trying to decide, like, do you want to have a lot of smaller packages, or do you want to have one big one? So in terms of advantages, you get a lot faster build times, right? So there's one of our larger repositories, and this is the one that has a lot of the old C++ primitives. It takes about 1 to 2 hours to build. And that's including the building and the testing. And so that contains the images, the detections, the catalogs, display, math, statistics, geometric objects, coordinates, and file handling. And that package is the biggest pain to work with, just because anytime you make any change and you have to compile it, it takes forever. And so so I know myself, and I think a lot of other people tend to not have to work in that package actively if they don't have to, just because of, that's such a large deterrent. Part of that is because that's not just the compile time, but the way that they set up the environment with scans, is compiling and testing is all done at the same time. So if the tests don't run or don't complete, then the build doesn't complete. And so, of that 1 to 2 hours, probably about 20 or 30 minutes is the actual build, and then the rest of it is running the test. Another advantage to small packages is less frequent rebasing, right? So because, any one package only has, usually only has a few core developers. And so, it's much less common that you'll have somebody else kind of touching the same areas of the same package that you do. And so, but the ones, the parts of the package where a lot of people touch, those are the ones that are a bit more difficult to update. It also makes a really easy division of ownership, right? So usually there's like one person who's kind of in charge of each package and oversees it. And so when there's changes to that, it's really easy to set up a division of labor so that you're not getting, pinged with, GitHub messages all the time. You only get them when they're things that you care about more. Okay. So disadvantage of a lot of small packages, if you have a large PR, like a large pull request that's across multiple packages, that can cause a lot of conflicts, right? Because sometimes what can happen is so maybe you'll have like 5 different packages, and you have to go and first you have to make sure that you've merged every single one of those PRs. And it's not uncommon for somebody to, if you've got like 9 different PRs to merge, you go and you think you got them all, but then you missed one of them. And then the entire stack's broke until somebody catches that, and you have to go back and fix it. What's less common, but does happen sometimes, for example, the PyBind 11 port, which touched, roughly 100 packages. We basically just had to tell everybody, don't merge any PRs for the next couple hours until we get everything merged and make sure that everything's been merged and building correctly. And so, that doesn't happen often, but there have been a couple different, kind of larger tickets like that where basically you just have to tell everybody to take the morning off. Because if somebody merges something in the middle of that and it breaks something, it can be a huge pain to go back and figure out what happened. Because that's a really difficult error to trace back. And testing is still done on the entire pipeline. And so that means, we use Jenkins for our CI, and it still has to build the entire stack, which means it has to pull all of those repos in it and build it all together in on the server. And so it doesn't save you as much as you necessarily think it would by having a lot of small packages. And so until recently, when we started creating binaries and had a Conda Forge environment, installation was very difficult. And so I'll kind of talk about that briefly. So when I was in graduate school, I actually was doing some data processing and everything. And so I thought about trying to just install the LSST stack before I was working on the project. And I worked on it for about a week, and then I basically gave up and decided to just write my own pipeline. It was that painful. And then when I joined the project in 2016, it took about 3 to 4 hours to rebuild the entire stack. And you had to do that about once per week. So that was kind of, I've shown the obligatory XKCD comic here. So building the stack was basically our code compiling. And, kind of Monday morning for the first 3 or 4 hours, like everybody's just kind of sitting around talking because we're all rebuilding the stack to be able to work that week. But then in 2019, we moved most of the third-party packages to Conda Forge, so we don't have to keep updating those in the GitHub namespace anymore. And they started creating nightly builds. And so now you have a binary that you can just install in a few minutes. And so now there's binaries created daily, and then there's also weekly binary builds that are on a shared server environment. And so I very rarely have to build anything these days. So as far as tying everything together, though, we use the extended Unix product system, or EUP. And again, remember, this is before virtual environment. This is before Anaconda. And so this turns out to actually still be a really good and a really powerful system for keeping multiple versions of packages at the same time. So essentially the way it works is all of the dependencies for any given version, well, for any package, are stored in a table that looks like this. And so there's just a table file. So the package has an ups directory. And then in that table file, it just says, you just basically declare all of the different packages you're dependent on. So this is kind of like your setup.cfg in Python. But again, this is a mix of kind of both C++ and Python packages. And it keeps track of those by version. So every time you do an install, it's installing that in an isolated environment. And so whenever you switch to a different tag, like if you have a get version tag, it automatically does all of the accounting to essentially know which versions of all the different packages you need. And so it's really convenient because it allows you to, say that I have like one package and I want to check out a version of it from 6 months ago. It'll check out the exact same version from everything else. Again, very similar to kind of what Conda does, but all of this was put in place long before that. So again, the advantage of that is that you can set up and you can unset up packages. So you only have one environment, but you can, and so that is kind of nice that you don't have to be switching back and forth between environments. You can have just one single environment, but then you can just kind of check out different packages and using different versions. And so, once you've kind of learned to use the framework, it makes it really easy to be developing, on top of things. The disadvantage is it's not really user friendly, right? This is something that was developed at Fermilab, and it has never kind of had a very high bar of trying to be user friendly. It also, another big disadvantage is you can't use Python setup develop if you have any C++ code, because of the fact that it's installing all this stuff in an isolated place. Once it builds those, all of the code, that's put in a separate directory that's not in your local Python directory. And so that can make it, kind of really inconvenient if you had to update the C++ code as part of your PR. And then it can be very slow on systems with a lot of old versions. And so they've gotten around this by just not keeping that many old versions. But the whole package is written in Python, and it's not very efficient at, again, right, there's 400 some odd packages that have different versions kind of all over your OS. And so all over your file system. And so, trying to keep all that together is, it can take several minutes just to import this, to do the first import of the stack, for example. So keeping track of versions, there's actually just a YAML file. And this is kind of the master YAML file that has all the packages that are, not third-party packages anymore, essentially. Mostly, there's still a few third-party packages in here. So you see for each package, it has the name of the package. It has the URL for the GitHub repo. For some of these, so like, for example, let me find one. So here's one that I help maintain. So I actually have a third-party package that I maintain outside of the stack. And so for this one, we wrap the third-party package, but then we just use a separate branch. And so so we also give a reference to what is, essentially the main branch inside the stack, and that's this LST dev branch. Documentation. So for the first 10 years, it was almost exclusively scientists developing this. And if any of you are scientists or work with scientists, you know that they in general are terrible about documentation. And, so in the first 10 years of code, there effectively was no documentation, or at least no useful documentation. And so all new PRs, we use the NumPy doc strings and have make sure that the code's well commented. And then there's work being done to go back, but there's so much old code that there's some things you just kind of have to know somebody to know what it does, unfortunately. But part of one of the things that's changed is, now everything goes through code review. So we don't have any PRs that aren't reviewed. Like everything is reviewed first, and all developers are reviewers and can be reviewers for a piece of code. And so it doesn't necessarily have to be, and usually isn't the person who's the main person responsible for a given package. It's usually just somebody else on the team will review the code, and then you'll often have the package manager just kind of overseeing things too. And then all of the code has to be rebased before merging. And so it sounds like Josh gave a good talk on Git last week. If you don't know the difference between rebasing and merging, I don't know if Josh talked about it at all. The nice thing about rebasing is when you look at the commit history, it looks like this. So essentially, every time there's a merge, you see all of the commits that were affiliated with that merge. And so it's really easy. You have this nice linear progression. If you do a merge without rebasing, then depending on when all these commits were made, because these are being done by different people at different times, they can be all mixed up and jumbled up. And so it's real, it really comes in useful, and you can actually force GitHub and Git to not allow you to merge code into the master repository without being rebased first. And that's essentially the way that they've set all of the repositories up. So one thing I get a lot of questions about is how do you configure a pipeline? Because I know a lot of people are writing their own pipelines, and this is kind of like when I've written my own, this is one of the big things. It's like, how do you keep track of the parameters that you're running and persist those to make sure that you know what configuration you used on any given run? And so this is one of the few packages in the stack that actually is a standalone package, and that's this PEX config package. And so each task is associated with a config class, and that contains all the configuration options needed for that task. And I know people on the project who use this in their other software projects outside of outside of Rubin. And so you have a YAML config file, or you can have command line arguments that are used to set the config parameters. And so essentially the config looks, something like this. So you would have a config file, you would have a config class, and then in that class, you can declare all the different options. And so you can give them default values, you can say what type they are, you can give them a doc string. You can have, if you have something that's like a list, so you can have something that takes in a list. And you can restrict what the values in that list are going to be. If you have something more complicated, that's the next part. Okay, sorry. So you have the config file, and then when you actually have the task, you just set, what's the configuration, what's the config class for this task, and then that gives you access to all the config options in the task. And so the way the pipeline works, this is actually kind of something ongoing. They just made a change in the way that the pipeline runs and builds. And so it actually builds a quantum graph. So once you pass it a set of a configuration file that tells it the pipeline that you want to run, it builds a graph that has all of the inputs and outputs. And so it keeps track of what needs to be done before each different task can be run. And so, for example, I work on the Blender, which just kind of takes pictures of stars and galaxies and tries to separate, the light from a star on top of a galaxy or two galaxies on top of each other, so that we can make measurements on both of those independently. And so that requires, the co-added images to be built. That requires a catalog to be built. And so it has a whole list of inputs. And so when you tell the pipeline to run, this is all being done on a CPU, on a server. And so, this is going to be done on multiple cores on multiple nodes. And so it makes sure before it starts any given task that all of the tasks before it that have completed to develop the inputs that a future task needs. And so it actually has a PostgreSQL database that they use to keep track of the quantum graph that keeps track of when different commands can run and running those commands. And so an actual pipeline file, so that would be something like this. So you would have, for example, this is the pipeline task that you want to run. And so then you have a list of inputs. So these are all the different files that you need to input into that. And then these are the outputs that it's going to generate. And so it can take that to build the graph. And then this is basically the entire LSST software pipeline. It's just a collection of tasks like this. Some of the default config options are overwritten. And some of these you'll notice. So for example, so this is one task, and then it has a bunch of multiple subtasks. So like the detection task, merge detections, the blend, measure, those are all tasks that are already defined up here. And so then you would have just one pipeline that says, okay, now we've got kind of this is our master list of all the data release pipeline tasks. And then you have a YAML file that essentially looks at each one of these tasks, and then builds it with any special configuration options you need. And so this is how, if you were to run your own pipeline, you would essentially build a YAML file like this, and the pipeline knows what to do from there. So that's not the part that I work on. Mostly I work on actually writing the software that's doing the analysis. But this is something they just recently done, and it's really cool. It's much better than the way the system was working before. So the other thing that I was going to show, but I got kicked off the servers. Give me just a second to see if I can get back on. Of course, we use multi-factor authentication, so it's harder than it should be. Okay, so to actually interact with the data and do anything, so again, there's going to be about 200 petabytes of data by the end of the 10-year survey that's hosted at Slack. And it's available to access for all US researchers using a Jupyter Lab environment. So essentially, you have an environment where you can pick the different build of the stack. So this is the weekly 16 build. So this is essentially this last week's build. But it has every weekly build that's ever been made. It has the daily builds from the last 2 weeks. And this is kind of some of the earlier versions of the pipeline that they had. You choose a container option, and then you can connect to the data. And once you do, it's basically like you're in a Jupyter environment, which is really convenient. Let's see what else I was going to say about this. Yeah, and so we're already using this to kind of test this out, and also it's really convenient because we have a set of data from the Hyper Supreme CAM that's kind of similar to LSST data. And so it gives us a place to test all our algorithms and everything that already has a large collection of data. And so you get this environment where you can have all your Jupyter notebooks. You can import everything and connect to data and see the images and everything. Okay, so the last thing I wanted to touch on is kind of like some advice I have on anybody else who's working on pipelines. Things I like, things that I would change. So one of the things that I would change is I would have a lot more focus on making independent packages that can live outside of your pipeline. Because with this pipeline, like everything's kind of dependent on everything else. And so it really, in a lot of ways, it defeats the point of having a lot of smaller packages, because all of the smaller packages all depend on each other and have these, kind of circular dependencies. And so I would say if you want to go a route where you're having a lot of independent packages, you should really try and make those as independent as possible. And if you have things that they all depend on, try and maybe make a couple larger primitive packages that you have, kind of toward this, further upstream or downstream, whichever stream is the, everything depends on. I would also, obviously use a lot less C++. In a lot of cases, there's what I would call just gratuitous C++. It's really there for no reason. It takes forever to build. And I found, just a couple of weeks ago, there was a piece of code that we've been using for a while, and it just seemed slow to me. And I rewrote it in Python using NumPy, and it was 2 orders of magnitude faster. So just because something's written in C++ doesn't mean it's faster, especially if it wasn't optimized very well. And so what I would argue for is better use of C++, right? So I would say, like right now, C++ is kind of the core of the stack with Python features downstream. I would make kind of the core and everything I could in Python. And I would only use C for things where you really need it to be fast. Like if you have, nested loops and things like that. And try and have as few as possible classes in C++. Like everything should, for the most part, be in Python. And just your functions that you need to be fast, you should write those in C. And if you do that, it saves you a lot of time in build times. It makes your code more readable. It makes it easier to maintain. It makes it much easier trying to just use something more standard like Anaconda instead of having to use kind of all these weird packages that we use, just because of the nature of the entire pipeline. I would also, urge kind of more frequent refactoring, especially when there's better third-party software. So, there's a lot of things in our code base, and astronomers are kind of known for this anyway, of just keeping code around for ages, just because nobody wants to rewrite it. And so, for example, the catalogs that we use are really slow. They're more difficult to use and slower than Pandas data frames or RocPy tables. Now, again, these were written before both of those, but there's been 10 years, kind of since then that they could have been upgraded, and they hadn't, and now it's kind of too late, and we're kind of stuck with those. But if they've been keeping kind of better tabs on the different pieces that we use, it really would have been good to kind of refactor more often. For example, for part of the reason a lot of our image processing is slow is because they use a footprint class that probably made a lot of sense in the 90s when there were memory issues, because essentially what it does is instead of storing everything as a square array, it stores everything as just kind of individual lines in the y-axis, like a one-dimensional array in the y-axis. But in order to do anything with those with images, it basically has to convert it back to a 2D array anyway. And so like things like that just really don't make any sense now, and probably should have been stripped out a long time ago. And then the other piece of advice I have is, we should have been creating daily and weekly binaries a lot sooner. As I said, my first, couple years on the project, I spent 3 to 4 hours every week rebuilding code. And so just think about across the, there's probably about 30, 40 developers across the project, 3 to 4 hours a week over, 3 to 4 years. That's just a lot of wasted person hours. And so even though there's, kind of that initial commitment that you have to make to getting all this done initially, and there's a bit of upkeep, the amount of time that you waste by not doing this, if you have a really large code base, I think is much worse than just kind of biting the bullet and doing it earlier. So thank you. That is what I had to share.
Thanks, Fred. That was really awesome.
That was great.
Cool. Thanks. All right.
So if I can jump in with a question.
Yeah, go for it.
So looking at that one config YAML file, it looks like you're still maintaining your own copies of packages like SciPy, NumPy, and stuff like that. Why are you doing that as opposed to, like, typically what we do is we just pin to a specific version that we know works.
Mm-hmm.
And then we don't have that extra overhead cycle of maintaining, like, releasing a new version that we know is good or something like that.
Oh, that is what we do now. So I did notice that as I was scrolling through that those are in the YAML file.
Okay.
But it actually uses the Conda Forge environment. So, and we do exactly that. We pin the different versions of those packages, and we probably somewhere in that file there's something that links to the Conda Forge repo. But you're absolutely right. That was a complete nightmare to have to keep track of things that way.
I mean, I admire you for keeping up everyone else's packages and all that kind of stuff, but why do it if you don't have to? Well, yeah, I mean, like you collectively, but yeah.
Yeah.
So in terms of the refactoring thing, what advice do you have? Because I have a code base at work that's a mix of old Python 2.7 that no one wants to bother to update because, well, it's still working and Lambda hasn't killed the support for it yet, and that kind of stuff. And it's like, okay, I got to convince these people that it's better to bite the bullet now than pay the pain later or whatever.
Yeah, right. I mean, that's exactly the thing, right? Is that I guess the argument that I try to make, and sometimes I've been successful and sometimes I haven't, is that it's going to have to be done eventually, right? Like a lot of those things, like you're going to eventually hit the point where you have to do that. And the sooner you do it, the less likely there is that you're going to have something that's going to affect the production environment, right? You don't want to hold up production because something you should have done 5 years ago just wasn't done because nobody wanted to do it. And that essentially is kind of what happened with the Python 3 port. Like you have no idea how strongly people were trying to cling to Python 2. And that was kind of like the thing that I walked into the project on, and kind of quickly got on the Python 3 side and was like, look, you don't want to have a packet, you don't want to have your entire pipeline based on a version of Python that's already outdated before a 10-year survey starts, let alone maintaining it after that. Like, it just didn't make any sense.
Fortunately, our core package is 3.9 at this point now, and there's a strong push to just keep upgrading that one there. It's just all of the other little ancillary services that we rely on, but they're kind of forgotten about because they just run in the background, and trying to get people to do something with them is tough.
Well, so another point I think is worth mentioning is, because of a lot of this legacy C++ code, so we've got about 2 years until the telescope comes online, and I could really use another person working on the part that I work on. And I went and asked if we could try to find somebody, and they said there's no point. Like, it would take so long to get them up to speed. They said, essentially what they've noticed is to get somebody useful takes about a year. And so it is literally like now we can't even hire people because there isn't enough time to get the work done. Whereas, you know, again, like 5 years ago, if you strip out all of these weird primitives and you make everything using NumPy and things that people use, then you can just hire developers that use the more standard tools. And so that's my main argument, is like, if you're using something that's specialized to you and it's working, then fine. Let that thing do it, and it's going to crash one day, and we'll deal with that. But if there's now like a standard version of that like a lot of people know how to use, and it's fast and it's well maintained and it's optimized, you know, make the switch as soon as you can, because that's the thing that you really pay for.
We've got one service we rely on that was written in Go, and the only person that knows Go left the company about 6 months ago. So now it's like, please don't break, because then one of us has to go come up to speed on Go and learn how to do it and all that. So same
Right.
idea.
Yeah, I have some friends that swear by Go, but if we had anything in that and it broke, then yeah, you got to figure it out.
So I'm coming kind of dominating here, but I do have another question. But
No?
if someone else has something, go ahead, please.
Go for it.
Okay. So I worked, previous to this job, I worked at a firm doing data engineering kind of work, and we were looking at a tool called Airflow that was very much set up on the idea of processing data in a series of stages, kind of like what you're talking about. And, you know, it would, you know, data comes into the pipeline, you would set a series of transformations that would happen in order and could kick off all these other projects. You know, I know when you started, a lot of that stuff was, you know, years in the future or whatever. Have you considered at any point like porting your systems to something that is out there? It's an Apache open source product, so it's, you know, fairly well standardized and so forth. That again would get you into something where a lot of people are going to be able to do it. You can also break up your code into smaller pieces.
Yeah. So I don't know if you know a lot of astronomers. They tend to like to do things their own way, and like again, like for me, it's kind of funny. Like if my colleagues knew I was giving this talk, they would laugh, because they know that I hate this like stuff so much. Like all this organizational like this is like it's a necessary evil, and so like I know it because I have to know it, and I understand it, and I appreciate that there's other people who like thinking about this, not me. But yeah, this is not something that I typically think about. For the people that do, I mean, again, they just redid our whole middleware system, and so I imagine that they looked at other things. I don't know why they ended up going with, you know, essentially writing their own middleware. But for whatever reason, they felt like there were things that we needed to do, that there wasn't a solution out there. I find that hard to believe, because there's so much, like, it's not like you know, I mean, we're processing a lot of data, but it's not like this is any more than Google or Facebook or, you know, Amazon or anybody else. So
yeah, that's it. I mean, you're doing different types of data, but it's still the same idea of a pipeline of processes that are going to run on a data pipe. Yep. Cool. Thanks.
Yeah. Mm-hmm.
Hey Fred, my name's Mike Frowns. I'm kind of a self-taught beginner, so I have a couple questions outside of code. One is, the name of this is Rubin. Where's Rubin from?
So Vera Rubin was an astronomer. She discovered some of the first evidence of dark matter, and so the original telescope project was called the Large Synoptic Survey Telescope, and then so the LSST, and then 2 years. And so typically, whenever they make a new telescope, they name it after somebody, but not initially. So like the Hubble was originally just called Space Telescope, and then with space telescopes, they don't name it until it gets launched into space, just in case it blows up, usually. And so after it got launched, then they called it Hubble. You know, so there's also the James Webb Space Telescope. There's the let's see, it was W first, now it's the Nancy Race Groman Space Telescope. and so yeah, so typically these things get named after somebody who was a prominent astronomer or person at NASA.
One last thing, you mentioned that the data is only available to certain folks. Do you happen to know if you're going to be able to get images? You know, like for my living room?
Oh, that's a good question. I think so. I don't know exactly how they're doing that, but I think basically because this is all paid for by the NSF and the DOE. And so essentially US citizens have right to all of this. Now, and so there's a few different answers to that question. So the one is there's kind of the portal that, you know, professional astronomers will use, and, you know, that they'll be able to get logins and stuff through their institutions. I imagine, again, because this is all paid for by all of our tax dollars, like if you wanted to have access to it, there's probably a way to do that. And I'm sure there's somebody who it's their job to figure out how to make all that work. The other answer to that is there's also, one of the interesting things about this project is from the very beginning, there was an education and public outreach group that is, you know, managed just like the rest of the project. And so they have been working on a separate set of tools that are kind of much more user friendly and much more kind of like touch and drag, you're more used to on the apps of your phone and everything. And so, you know, if you just kind of want to go exploring around, you know, space for a while, like they'll have tools to do that.
Okay, thank you. Thanks a
and
lot.
I think, sure. Yeah, I think they're even building like educational modules and stuff so that you'll be able to like, I don't know the details of it, but I've heard, you know, it described, you know, essentially like if you to teach you about galaxies or stars, and then be able to do that by like giving kind of a tutorial as you can click through images of galaxies and stars and everything. So it should be pretty cool.
So this telescope is doing a survey of all the southern hemisphere. What's the northern hemisphere equivalent of this project?
So there isn't one, actually. It's interesting that a lot of the good observing is done in the southern hemisphere. There aren't a lot of good locations in the northern hemisphere. You know, you pretty much need kind of dry and really high and a stable government that's friendly to the US or the European Union to put their telescopes there. And, you know, kind of most of the, you know, Europe, it's just all cities. You know, the US is mostly cities. You know, or you know, like Canada just doesn't have a lot of doesn't have high mountains to put it on, for example. And so yeah, there's some observatories in the Canary Islands, and I think that this is where they're building one of these, 30-meter telescopes. Like, you know, these things are going to be enormous. But yeah, there isn't really an equivalent for this in the northern hemisphere, where we get by basically on the sense that for the type of astronomy that most people want to do with this, the galaxy, the universe is basically isotropic. Like, it's kind of the same in all directions. And so by looking at half of it, while we won't know the details of what's going on in the other half, we'll know kind of qualitatively what the universe is like.
And from Chile, which is relatively close to the equator, you're going to actually be able to see quite a bit into the northern sky,
yeah,
and all the way to the southern pole too. So you're covering more than half the sky there.
Yeah, that's true. That's a really good point. Yeah.
Will the data from this project be integrated or combined with all the other digital astronomy that's going on?
Yeah, so that's what I was hitting at the beginning of the talk, is that, like, there's going to be very few astronomy projects, you know, in the next few decades that don't have some component of this. Because even if you're making observations from space, the telescope's going to have different filters, and so there's going to be typically what happens with a space-based telescope is you have a really high resolution camera, but not as much time being able to look at a single place, because like, you've got a telescope, and so you're essentially kind of doing orbits. And, so for part of the orbit, it's kind of looking at your object, and, so it has to move and stay focused on the object, and then it goes behind the Earth, and then it comes back and does it again. And so the images typically aren't as deep. And so you can get more detailed on the brighter things, but you can't see as faint of things. And so for the fainter things, you need more coverage from the ground. It's just going to be fuzzier. And then, you'll have people doing like, X-ray projects using X-rays. You'll have people that have, universities that have their own telescopes that will supplement it with data from the LSST. And so, typically these days, when you make an observing proposal, you're usually not just using one data set, you're using a lot of different data sets. And so there's 3 or 4 kind of all sky data sets that we use right now. And then this will just kind of be the big one, that comes next.
How did you get involved in this project?
So that's a good question. So when I actually went to graduate school at the University of Rochester, and that's how I know Rich and Josh, and how, I've attended all these RocPy meetings back then. And it's success in academia. It's partly based on skill and partly based on luck. And I happened to be working on a project where we had images from a different large camera that my advisor had taken. And, there were about 20 million objects in it. And I had to go looking for, about 500 interesting stars, these substellar objects called brown dwarfs. So it's basically kind of like something between the size of like Jupiter and the small sun. And so, I had to write my own like big data analysis pipeline to find these things and to take the images and look for the types of stars that I was looking for and everything. And just when I was getting ready to graduate, Princeton put out a job ad to work on a pipeline. And, they had like all the qualifications, it would be nice if somebody had this and this and this and this. And I was like just checked off every box from my thesis. And so I was just like, it just happened to be the right place at the right time. And so they were hiring people there, and that's where I went.
Nice.
Was your PhD in astronomy or computation of some sort?
Yeah, it was in physics and astronomy. So I actually spent the first half of my PhD doing theoretical high energy physics, and then switched to astronomy because I wanted to be employed after I got out of graduate school. Basically, like my daughter was born as I was studying high energy field theory, and everybody I knew in that field was like unemployed or working on Wall Street, and I didn't want to do either of those things. So I switched to a branch of physics that would give me other skills. So if I couldn't continue in academia, I'd be able to kind of translate and
switched out of astronomy into computers so that I would be employed and be able to pick my life.
Yeah, well, there you go.
All right. So that looks like we're wrapping things up here. Thank you very much, Fred. That was fabulous.
What's up? What's new with you?
Oh, lots of craziness at work. Oh, got the tree fort and zip line completed.
I saw some pictures of that. That's pretty cool.
Yeah. It came out really good. And we got it all tightened up now.
You got a what?
We got the zip line all tightened up now. It's all nice and taut.
That's pretty awesome.
Yeah. It's been a big hit around the neighborhood.